This is a series of seminars from ENERCOMP. Today we are presenting the seminar series about performance and integrity track of composite and joints. So today we have Dr. Ali, who is teaching us today on the durability of adhesive joints. Dr. Ali obtained his PhD in mechanical engineering 2017. Since then, he is a coordinating researcher at INEGI, Portugal since 2018. He had a very good profile, over 150 papers with H-index 28, many conference presentation, recognized as a world top 2 scientist. In 2023, many chapter books and conference presentation, conference organization, and he also participated as editor in some journals. Dr. Ali is part of the group from Professor Lucas da Silva, who is a full professor in the Department of Mechanical Engineering at Faculty of Engineering, University of Porto. He has a PhD degree in structural adhesive bonding from Bristol in 2004. He leads the advanced joining processing unit at the Institute of Science and Innovation, Mechanical Engineering and Industrial Engineering, INEGI, composed of approximately 40 members of postdocs. He is coordinating more than 25 research projects funded by different funders. He has published more than 600 articles and 43 books. He is an editor for several journals and editor for many books as well. So it's a very well recognized group in the area of adhesive bonding and this techniques. So today they will present us their work on durability analysis of adhesive joints. They will talk about the advancement, challenges, and a path for implementation. This is one of the key parameters that we look for in ENERCOMP for the performance of adhesive joints. So welcome, Dr. Ali, welcome, Professor Lucas, and thanks for joining. The floor is yours now to start.
So, Professor Lucas, do you want to say something, or I can start?
I just want to say thank you for having us today. It's a pleasure to be with you, and I hope you enjoyed it. Thank you very much.
Thanks, Professor.
Okay, yeah, thank you, Ahmed, for inviting us. If you don't mind, I can share my presentation and start the presentation.
Please go ahead.
So, can you see my screen?
Yes.
Okay. Good morning and good afternoon, everyone. My name is Alireza Akhavan-Safar, and I'm a researcher at the Advanced Joining Processes Unit, led by Professor Lucas da Silva, as Ahmed correctly mentioned everything in detail, and thank you for your introduction, Ahmed. AJPU, our research unit, is part of INEGI, which is located at the University of Porto in Portugal. And first of all, I would like to thank the organizers of this seminar or webinar, and in particular, Dr. Ahmed Waqi, for inviting us to share some of our group's experience in the field of fatigue in adhesive joints. Adhesive bonding actually is not the only topic that in our group's activities, and our focus is broader, and we work on a range of advanced joining processes, including adhesive bonding, welding, and joining by plastic deformation. As Ahmed also mentioned, and the title of my work also suggests, this seminar will focus on understanding the fatigue behavior of adhesive joints and assessing their service life under cyclic loading, a subject of great importance, but still one of the major challenges in industry. So this is actually the outline of my my presentation. My presentation is divided into several parts. I will start with a short introduction highlighting the importance of accurate material characterization, particularly for adhesives, and most importantly, their fatigue behavior. Next, I will discuss fatigue in adhesive joints from the SN perspective, and then I will move to the topic of fatigue crack growth in adhesive joints, which remains a very, very challenging area. And finally, I will introduce two novel tools that aim to overcome several challenges that we have in fatigue life assessment of adhesive joints in industry. A correct selection of material, correct and reliable design, a well-planned and schedule properly the maintenance and repair, and for development of accurate models for predicting adhesive joint behavior. We all of these need an accurate and reliable material characterization. So material characterization is the key. Characterization generally involves two main stages. First is selecting the appropriate experimental setup, including choosing the right specimen, defining the boundary conditions, setting up correctly the loading condition, and selecting an appropriate measurement instrument. If everything goes well, then we will have the raw data, but the next important step is to treat this data. And this is one of the most critical steps in obtaining accurate material properties. And a poor choice in data reduction can easily, data reduction method can easily lead to inaccurate estimation of the material's behavior. When these steps are performed correctly, then we have everything ready to perform a simulation. And in case we select a suitable numerical model, we will be able to simulate the material's behavior in a way that matches the experimental results very closely. If any of these stages fail, it means that we will have the material poorly characterized. Poor characterization leads to inadequate design and poorly planned maintenance and repair schedules for adhesive joints, which in turn increases the risk of joint failure during service. Such a failure can even trigger the collapse of the entire structure, which is, of course, can be a complete disaster. Characterization can be even more complicated when the loading is not static, but fluctuates over time, which is common in real structures. In this case, fatigue damage becomes the main concern. And if the loading is of variable amplitude, which is the most common loading condition in practice, then characterization can be even more complex. Now, imagine your structure is in a humid environment, then you must take into account the effect of humidity, of course, especially for adhesive joints, because adhesives are really sensitive to humidity. And if we make the scenario even more realistic, this moisture level may also vary cyclically, meaning both the loading and environmental conditions are cyclic. You can imagine how complex it becomes to characterize the adhesive's behavior and predict fatigue life under such complicated conditions. And on top of that, of course, we have temperature. In practice, the joints are subjected to a wide range of temperature in service, very low and very high temperatures. And we have to take into account the effect of temperature in addition to all the other parameters that I just mentioned. Our research group, Advanced Joining Processes Unit, has already completed successfully several projects and is currently also working on multiple industrial projects dealing with fatigue in adhesive joints. These projects have been carried out in collaboration with leading industrial partners, ranging from adhesive manufacturers to end users in various industrial sectors, such as automotive, energy, agricultural, machinery, aerospace, steel, electronics, and even semiconductor industry. Okay, now let's talk a bit more about fatigue in adhesive joints, and I'm going to share with you some of the results that we have obtained so far actually in these projects. Fatigue in adhesive joints can be analyzed from two different perspectives. The first one is SN approach. Here we should obtain a master SN curve. That's the key part of SN approach methodology. And with the help of finite element analysis, plus this master curve and plus an effective parameter or fatigue parameter that we should develop or we should select correctly, we will be able to predict the fatigue life of adhesive joints in real practice. We also have another scenario, another approach based on SN still, but without this master curve, we will have ideas about the fatigue of adhesive joints based on SN approach, but I will talk about it shortly. On the other side, we have the fatigue crack growth approach. Here we have a Paris law curve. Again, similar to SN approach, here we should develop and construct a master Paris law curve. So to obtain the master Paris law curve, it's really important to select an appropriate Paris law parameter. So similar to SN methodology, the challenge here is to understand what's the suitable and appropriate Paris law parameter. In case we select a correct one, then we will be able to collapse all the Paris law curves obtained for different loading and environmental event conditions into a single curve, which we call it master Paris law curve. Now I'm going to start with SN, and I will share with you some results based on SN approach, and then I will continue with fatigue crack growth approach. The SN approach actually can be implemented in two ways, direct and indirect. In the direct method, you test the real joint to obtain the fatigue life directly from the test and without any specific post-processing. In such cases, usually you need to test a full-scale structure. So it's an expensive test and requires specialized equipment and gripping systems. But the good point here is that it doesn't rely on simplifying assumptions, and it captures the actual fatigue life of the bonded joints. However, the direct method doesn't actually characterize the adhesive itself. Instead, it only evaluates the fatigue performance of that specific joints within that particular structure. So as a result, the findings are limited because of these specific applications, and they are limited to this application, and we cannot use the data or the results for other joint geometries or in other structures. On the other side, we have the indirect method, which is significantly less costly and doesn't need special testing equipment. However, it relies on multiple simplifying assumptions that this may introduce errors into the final results that we have obtained. And in addition to that, a challenging post-processing step is also needed. And I will discuss about indirect method in more details in the following slides. But the very good point here is that in this indirect approach, we characterize the adhesive. It means that the results can be used for a wide range of structure, wide range of geometries, joint geometries, loading conditions, And we need to be very careful here, because in indirect methodology, we estimate the fatigue life and not obtaining the real fatigue life. But in direct methodology, we obtain the real fatigue life. Direct methodology can be a bit more simpler and less costly, where we can, if we test subcomponents or if we perform tests at subcomponent level. We have done this before in our group in some projects. For example, in one case, we replaced a welded joint with an adhesive joint in part of a boom structure here, used in agricultural or construction vehicles. And the company asks us to perform this and do this replacement and analyze the fatigue response of the welded joints compared to bonded joints. And interestingly, we found that the bonded joints can provide us a much longer fatigue life than welded joint, especially for high cycle fatigue regime. In another subcomponent level test, we have this actually bar tested under 4-point loading conditions. And this is part of a wind turbine structure. Also, this is part of another project, and the company wants to analyze the fatigue life based on direct method using a subcomponent level test. But again, you see that in both cases, we need a special apparatus to be designed, and the tests are a bit more expensive than direct methods at subcomponent level. Direct method actually can be simplified even more by testing a representative bonded joint specimen instead of a real subcomponent. For example, instead of testing the full boom connection, we could test or we can test a single lap joint, because actually here it's an overlap, single overlap joint here that can be actually we can use single lap joint instead of testing this. Or for skin to stiffener tests as part of a fuselage, for example, we can do the test on T-joints with the same substrate materials and adhesive. And another example is the repaired patch, usually composite patches used for repairing pipelines or even skins. And instead of testing a subcomponent level or full scale component, we can perform tests on a kind of oversimplified joint, which is scarf joint or double stripe joint. At this level, no special equipment is needed, and the results may be applicable to joints with similar geometries in other structures as well. And these are the good advantages of these oversimplifications. While we are still in direct methodology, but we are trying to simplify it a bit more to reduce the costs, reduce the time, and also be able to test using universal testing machines. But the thing is that we are simplifying the conditions, loading conditions, boundary conditions, and we ignore the interactions of these joints with other part of the structure. So when we interpret the data, we should take into account all these assumptions made in this actually type of direct testing. On the other hand, we have the indirect method. From the experimental perspective, the key difference in the indirect method is that you must test simple bonded joints under pure loading modes, pure mode 1, pure mode 2, pure mode 3 even. So, for example, a single lap adhesive joints is generally not suitable for this approach unless under some specific special conditions. In our work, we have used the Archon specimens for this purpose. And this specimen meets the requirements for fatigue analysis in bonded joints. Archon has the advantage that you can change the loading angle without changing the specimen geometry, without changing the setup, without changing the boundary conditions and joint type. And as I mentioned before, the most important challenge in indirect methodology is to actually select or develop an equivalent fatigue parameter or stress parameter that can take into account the effect of all the important factors that change the fatigue life of that adhesive. It can be as challenging as a 3 years PhD project. And that's one of the most challenging part of indirect method. So despite the very simple relatively simple test that we can perform in this method, but the post-processing part is very challenging. But as long as we have as long as we have this S-effective developed, then we are able to construct a master SN curve. Once the master SN curve is obtained, a finite element analysis of the actual joint should be performed, and the fatigue damage parameter S-effective here can be extracted from FE results. And by using the master SN curve, we will be able to predict the fatigue life of the real joint. But please be careful, because here we are talking about prediction and not obtaining the real value. This is another important difference between indirect method and direct method. Our research group has conducted several direct method projects as well, and in collaboration with various industries and companies. And I'm going to share with you some of these results. One of the most important parameters that must be analyzed experimentally when using indirect method is to analyze the effect of loading mode. So we have to analyze the effect of loading mode by changing the loading angle from pure mode 1 to pure mode 2. In several tests that we have performed on many different types of adhesives, we have obtained like a consistent finding, which is the highest fatigue life for pure mode 1 than pure mode 2. It means that if the joints are subjected to a pure mode 1 loading condition under cyclic loading, they can provide us a much longer fatigue life than pure mode 2, sometimes by factor of 10 or even more. It means that if a joint subjected to pure mode 1, if it lasts for 10 years, the same joint under pure mode 2 under the same fatigue load will last like 1 year only. So that's the huge difference between the life for mode 1 compared to mode 2. But we should note that in reality, stress concentration at the joint edges can strongly influence this result that I show here. And stress concentration can produce high peel stresses at the bonding ends or at the edges or at critical points of the joint. And that can significantly reduce the fatigue life under pure mode 1, not pure mode, under tensile loading. And that's why still shear dominant design is recommended. There are other reasons why shear loading is better than tensile, and why we have to design joints to be loaded mainly under shear than tensile. One of them is the effect of temperature. When we tested the joints under high temperature, we noticed that the sensitivity of mode 1 to high temperature is much higher than mode 2. This finding reinforced again the importance of designing joints in a way to be loaded mainly in shear. And another parameter that we analyzed is the effect of moisture. We have performed similar tests under humid conditions. Again, moisture causes a substantial reduction in fatigue life in both loading modes, of course, but mode 1 is much more sensitive to moisture than mode 2. And that's one of the actually reasons, again, that designing joints in a way to be loaded in shear is recommended. I talked about cyclic humidity in the introduction, and we have investigated this phenomena in detail in a PhD project in our group, and with several important findings. One key observation is that the moisture ingress rate changes from cycle to cycle and stabilizes after a few cycles. We found that the rate of water uptake, the diffusion coefficient, is much higher under cyclic loading than cyclic aging than constant aging. It means that if the environmental condition is cyclic, you will experience, or the joint will experience, a higher rate of degradation in properties than when it's subjected to a constant humidity level. And again, it means that for characterization of adhesive in terms of humidity under cyclic loading, for example, in case you perform a constant aging test for a joint that in practice is subjected to cyclic aging condition, you most probably will overestimate the service life, which is not good, which is dangerous and critical, a critical design. Another important finding is that the SN response of the adhesive depends on the numerous of moisture cycles. We saw a continuous drop in SN curve by cycles. For example, here is the SN curve for unaged condition. After the green one is after actually third cycle aging. And the blue one is for first cycle aging, and this is for third cycle aging. You see that after third cycle, actually the joint is almost dead. And when we dried the sample, we could recover the properties by nearly 50%. And we noticed the recovery also is a function of the number of aging cycles. The recovery after the first cycle could provide us this SN curve, but after the third cycle, we have just this green one. And we believe that if we continue aging for more cycles, then actually it will be difficult to have even a good joint even after drying and recovering the properties. In another study, we analyzed the effect of adhesive type. We tested joints with different types of adhesives from different families with very different static strengths and very different mechanical behavior under quasi-static loading conditions. As a general trend, you know that the lower strength adhesives tend to show a shorter fatigue life, but when we plot results against load ratio, which is defined as the fatigue load divided by the respective static strengths under the same loading condition, we see that there is no or big difference that we usually observe in the static results here for SN curves. It means that even without performing tests or experiments, we are able to have a very rough idea about the fatigue life in case we know what's the load ratio. Our group activities are not only concentrated on experimental studies, but also we have been active and we are active in developing fatigue life prediction models for bonded joints. And this is one of the most recent SN-based models that we have developed. And it's actually developed in a PhD project. I would say that this is one of the most universal fatigue models developed so far for fatigue life analysis of adhesive joints. And this model could provide us a good prediction of fatigue life for different joint geometries, Archon at different loading angles, different material and single lap joint with different overlap sizes, with different substrate materials, and even at different environmental conditions, humidity, and also temperature. And here you see the red line shows that shows the prediction based on this model, and the symbols and dots actually are the experimental data. Now I'm going to talk about the fatigue crack growth. As mentioned before, analyzing fatigue crack growth in adhesive joint is more complex than working with the SN method. Here, I'm going to show you actually some results and share with you some findings and insights. Here I show 2 examples of DCB joints tested under pure mode 1 fatigue loading conditions, and several phenomena are visible here in the adhesive layer. We have here a very ductile adhesive with 150 elongation at failure. This is a metaacrylate adhesive. And you see a very large widening area. This is actually a magnifying glass. We try to zoom a little bit more to be able to see the very thin layer of adhesive here. That the real size is here, hard to see the adhesive layer. But here you see that we have a crack here, a crack tip is somewhere here, and these are the large whitening area and process zone ahead of the crack tip. The energy here is spent partially in developing this large process zone ahead of the crack tip, and also for opening the crack itself. But we need to be careful here because the crack opens within an already damaged area. And so the energy that finally we measure out of this test is the energy of the system, both whitening and damage zone plus the opening. And then using this energy that we measure cycle by cycle, we can construct and plot the Paris law curve. On the other side, we have actually another DCB tested on pure mode 1 loading condition. This is not a very zoomed view. Actually, here we have a very thick layer of adhesive, 4 millimeter thick adhesive layer. And we have also several phenomena here. We have multiple cracks. We see a secondary crack here already propagated. Another phenomenon is the actually crack kinking. We see that this is the pre-crack, and the pre-crack doesn't propagate along the midplane of the adhesive layer, but it kinks towards one of the interfaces here. And we have not possible to see in this video, but we have a very large process zone here, damaged area here. With a crack is not actually created yet, but in the following cycles, we have another crack here created and several other cracks. So we have multiple cracking, multiple site cracking phenomena here. And that's why fatigue crack propagation analysis and characterization of adhesives in terms of crack growth is really a challenging task if you want to take into account correctly all these phenomena. We have actually analyzed fatigue crack growth in different types of adhesives, silicone, epoxies, metaacrylate. And I need to highlight this point that these adhesives are really different adhesives in terms of strength, elongation, even fracture energy in quasi-static loading condition. But when we tested them under cyclic loading, we see more or less similar slope in Paris law curves. And in this bar graph, you see that actually the slope changes from 6 to a bit more than 7. So that huge difference that we observe in quasi-static loading conditions and strength of these adhesives and elongation of this adhesive is actually are not observed in M values under cyclic loading. But as a general trend, we can say that the lower the mode 1 fracture energy under quasi-static loading condition, the higher the M value under cyclic loading condition. A similar conclusion holds for pure mode 2 loading, where we use the ENF joints for fatigue crack growth under mode 2 loading condition. And again, we can say the lower the mode 2 fracture energy under quasi-static loading condition, the higher the M value under fatigue. We have also conducted this test under various mixed mode loading angles. And when we plot M envelope for different mode mixities, we find that despite the large difference in static behavior among the adhesives that we have tested, their fatigue crack growth behavior doesn't differ significantly. And the M value more or less remain within a relatively narrow range for all loading modes. But a general trend for all mode mixity is that in case you have a lower fracture energy under quasi-static, you should expect a higher M value under fatigue. I mentioned before that in fatigue crack growth characterization, we need to search for a good Paris law parameter to be able to construct a master Paris law curve. And here are the results. And we actually did this test on a meta-acrylate adhesive. And by changing the Paris law parameter and by including the effect of R ratio, we were able to collapse all these curves into a single curve. And using this curve, you just need to analyze probably numerically the energy. And by knowing the loading condition, you will be able to know what's the rate of crack growth for all these loading scenarios. So you just need to test one of them, and then you can precisely predict the dA over dN for the other three. That's also very important when we characterize adhesives in terms of fatigue crack growth. We need to try to take into account the effect of all important parameters to be able to construct this actually master Paris law curve. Loading frequency is an important but relatively overlooked parameter in research. Fatigue life can be highly sensitive to loading frequency. And by increasing the loading frequency, the number of cycles at failure increases. While high frequency testing actually sometimes used for to make the running time, testing time shorter, but it can easily lead to misleading results and can overestimate or underestimate the service time. Here, for example, in our results, the longest service time occurred at 1 Hertz. And the shortest service time was for 10 Hertz. And when we analyze the adhesives under cyclic loading, and we are going to change the frequency and make it different from real practice, we need to take into account all these important points. As we discussed earlier, the Paris law consists of 3 main regions: threshold region, stable crack growth zone, and finally the unstable crack growth part. And we have 2 different strategies to analyze the fatigue crack growth actually in adhesive joints. The test can be load control or displacement control. And in load control, the test starts from a threshold region. Then we move to a stable crack growth part, and then finally the joint fails with an unstable crack propagation. In displacement control, the test starts with an unstable crack propagation. It moves backward to stable crack growth, and finally we reach a threshold region. And when we reach the threshold region, actually the crack propagation stops and the joint doesn't fail. In load control tests, usually we need to test several joints at different loading levels to be able to find a real threshold value. But in displacement control, only a single test can be enough to obtain the threshold. We have analyzed this parameter on adhesive joints, and we noticed that the choice of test method can lead to significantly different results for fatigue crack growth in adhesive joints. And our results for a polyurethane adhesive showed that the threshold fracture energy obtained for based on displacement control, this one, is a bit lower than the threshold energy obtained based on a load control strategy. No big difference, I would say, but when we increased the temperature to 60 C and we repeated this test, load control and displacement control, we see here that actually the difference between the threshold energy of load and displacement control, both of them are actually even more than room temperature. But the good point here is that for both cases of load control and displacement control, the M values were similar. And so in case that we perform a test under load control or displacement control, probably M would be the same for both approaches, but threshold might be different. And we need to be very careful, especially if you design the joints based on safe life philosophy. Our group has also previously proposed models for various loading modes to predict the fatigue crack growth in adhesives. All of these models are based on cohesive zone modeling. And compared to traditional SN approach, fatigue crack growth simulation and modeling requires more extensive testing and more knowledge, finite element knowledge, fracture mechanics knowledge, and it's more challenging. And we have also actually published a book on using cohesive zone modeling for fatigue life analysis of adhesive joints. This is one of the models that we have developed. One important point in fatigue crack growth analysis of adhesive joint is to understand and know how the fracture properties degrade cycle by cycle. This is an important parameter. Then by knowing this degradation rate that we have obtained this formulation for this to define the rate of degradation, then we know how to degrade attraction separation law used for cohesive zone based on cohesive zone modeling approach for predicting the fatigue life of fatigue crack growth life of adhesive joint. And here you see a comparison between numerical and experimental results. Okay, I talked about two different approaches: static SN approach and fatigue crack growth approach for characterization of adhesives. And I mentioned that these are actually really challenging tasks if we are going to characterize real joints in real scenario, in real world applications, in industries with complex structure and complicated loading conditions. But I'm going to talk about these challenges a bit and also solutions here. We know that adhesive joints are widely used in aerospace, marine, automotive, oil and gas structures, partly due to their relatively superior fatigue life compared to other joining methods. However, predicting the fatigue life of these joints actually is a challenging task that requires knowledge across multiple disciplines. And the problem is that we have too many models already developed, and we need to understand which one is the most appropriate one to characterize or to simulate or to predict the fatigue life of the joints that we have in our structure. A quick survey of the literature on fatigue of adhesive joints shows two important trends. First, it's clearly seen that here we see that the number of publications per year increases exponentially. That show the expansion of adhesive bonding applications in real-world industrial sectors. And the second point is that there has been significant progress in developing fatigue models dedicated to adhesive joints. But unfortunately, none of these dedicated adhesive joint fatigue models can be found in well-known commercial fatigue analysis software packages. On one hand, we are dealing with a complex phenomena in which fatigue behavior is influenced by many parameters and different loading and environmental conditions that can make the analysis even more challenging. And on the other hand, we have the fatigue adhesive joints, fatigue of adhesive joints, which remains a critical concern for industrial applications. So what's the solution? The solution, we believe, that is to develop special tools dedicated for fatigue life analysis of adhesive joints using models that are dedicated for fatigue life assessment of adhesives, and also try to simplify this task and this analysis as much as possible for end users in different industries. In July of this year, like for 5 weeks ago, we launched a consortium comprising leading edge companies from various industries. Within this consortium, our research group is leading a 3-year project, and we are going to develop fatigue life analysis tools, the ones that I just mentioned, and deliver them to the consortium members. The first tool we are going to work on and we are going to develop is called BondLife. BondLife is based on SN approach. It's an innovative software package specifically for SN-based fatigue life prediction of adhesive joints. And this software allows users to predict the fatigue life of complex structure with multiple bonded region and even different types of adhesives. BondLife provides users a list of fatigue model that user can select, and also there has been a material library available, along with several other tools and options and features in this software. So it will be a software for this specific purpose. The other tool that we are going to develop as part of this consortium is called BondCrack, that focuses on fatigue crack growth analysis in adhesive joints. It's going to be designed to minimize complexity and to enable users, even with limited knowledge of finite element software and fracture mechanics or even fatigue analysis, to still perform this simulation and predict the fatigue crack growth in real adhesive joints. The bonded structure, actually, that BondLife and BondCrack can analyze can be highly complex with multiple bonded areas made from different adhesive types and subjected to variable amplitude loading. And the consortium project also includes a comprehensive experimental program, not mentioned here because of the short time for this webinar. But this comprehensive experimental program will cover fatigue, static, and fracture testing of stiff and flexible adhesives. But the good news is that the consortium project has just been started, and it's really fresh. It started like a few weeks ago, and we are at the very early stages of this consortium, and we are still welcoming new members, new companies. And we invite companies who are interested in this topic to join the consortium and benefit from the advantages and products that will be developed during this project. And thank you very much for your attention.
Thank you, Ali, for the nice talk and interesting results you got. Well, the tools for fatigue life prediction that you develop and you presented at the end, it's really important, and it's really needed for the industry now. So during the presentation, we have a couple of questions that came from the audience. Well, the first question comes from, I think, Ibrahim. He's from Future Pipe Industry. It's one of the leading companies in the pipeline manufacturing and bonding of pipelines and so on. So he asked about, well, I will read exactly his question. So does this study also applicable for pipes? So it's expected he's working for pipes. So all what you present today, it's on a flat plate or a coupon that's flat. Yep.
Yeah, no limitations, no limitation. Of course, it's applicable for pipelines as well. And actually, while most of the studies and projects that we are running currently are more for maybe flat structures, but doesn't mean that it's limited to. And we have been working also on real structures, but yeah, no limitation, and it's applicable for pipelines.
Okay. Even if we consider the stress state in the pipelines, if you connect two pipes under the internal pressure that create axial and hoop stresses and so on, that we don't consider usually in the flat plates, this kind of let's say complex or triaxial stress state on the joint. Do you think this will affect the models you are working on, or just it will be the same, just we need to consider for a new stress state?
Yeah, it's just a new stress state. No big deal. Actually, the thing is that we have a list of models. In this, we are going to include a list of useful and appropriate models applicable for a wide range of applications. And in case, for example, in our consortium, we have members more interested in pipelines, we will search for a model that can actually predict pipeline fatigue life with more accuracy. So, and then the user can select that one. But one point that I didn't mention here is that we have also an option. We will have an option including in this bond life software, which is a model suggestion. It means that based on the user input in terms of properties, loading condition, and whatever, the software will suggest the best model that can be used for fatigue life analysis of that specific joint for that particular application. But no limitation in terms of stress state. We just change the stress parameters and at nodes, integration nodes, and that's it. So no limitation in terms of the structure that we can analyze, unless you have like failure in substrate, like in that case, since this software is going to analyze the fatigue in adhesive and not fatigue in substrate materials, so that will be another work, another study. But no limitation for pipelines in case we are worried about the failure in bonded joints.
Okay, thank you. We have one more question about the cyclic humidity test you presented. So the question comes from Shaulili. He is one of our colleagues in ENERCOMP. So he's stating that as you are testing the same sample, so do you think the degradation is from the accumulation from the previous loading cycle, or how you decouple the effect from the environmental and the fatigue loading process?
Yeah, maybe it was not clear if it's the case, so I'm sorry for that. I'm going to clarify this again. In cyclic aging condition, we had cyclic aging first before testing, so before mechanical testing. It means that we perform cyclic aging on many samples, and we took the samples out of this cyclic aging process at first cycle, third cycle, first drying, third drying, for example, and we tested them under cyclic loading, and we tested until the joint fails. And under cyclic loading, we changed the load level for different actually samples we tested. So that's why we could finally have the SN curve. I'm not sure if I could answer your question, but if not, so please let me know, then I can clarify a bit more.
I think just thanks for answering this, but I think the main point from Chaula that the sample now it faces two fatigue cases. The first one, the stresses that come from the humidity cyclic. So this is a thermal cycle that or a humidity cycle that you increase the humidity, reduce it, increase it, and reduce it. So this make a strength, or it will cause a little bit of strength degradation, let's say. The second process that you consider here, it's the fatigue loading. So you are loading, unloading, loading, unloading, which means that the sample or the strength will degrade also because of this. So the question here is, did you decouple, how we can decouple this effect? So if we have a 10% reduction due to humidity and 10% reduction due to fatigue loading, how we decouple this? Do you have idea about this, or I don't know if the question is clear?
Actually, the second part was not very clear to me, but the thing is that maybe I can explain a bit more. Here, you see my screen, right?
Yep.
Yeah, okay. So, for example, here we are talking about cyclic aging plus cyclic loading. It means that we perform cyclic aging first, and then we tested them under cyclic loading. Under cyclic aging, we have a degradation in properties. We have also static results. We have published this data in a paper, and we see a degradation in properties. And this degradation in properties is a function of aging cycle, of course. But after that, we perform cyclic loading, and we know that the properties degrade cycle by cycle until the joint fails, right?
Okay.
So the SN curve that you see here, we have a reduction in SN curve, is due to mainly due to the aging. So it means that in case you have more aging cycles, the rate of degradation will be higher, and you will have a bigger drop in SN curve.
Yeah, that's clear now. Thank you.
Thank you.
Yeah, again from Future Pipe Industries. So they ask, what technology did you use to detect the failure? Is it only visual inspection? I think it's in the videos you present for the fatigue, how you detect the crack.
Yeah, no visual inspection. It's hard to detect actually like here. Yeah, it's hard to detect the crack propagation visually. And we need to use a very specific data reduction methodology. We use a compliance-based method, which means that we analyze the rate of increase in the compliance of the joint cycle by cycle, and using this compliance this increasing compliance or reduction in stiffness of the joint, we have an accurate idea about the crack size. But in such cases, in such complicated conditions, we have to consider an equivalent crack size, meaning that we need to take into account the effect of damage zone as well, because the total energy that we are spending for crack propagation is partially spent on the development and evolution of the damage, and part of that is for opening of the crack. But as I mentioned, the crack is not opening in like an undamaged zone. We should have a damaged area first, and the crack is opened in an already damaged region. And yeah, so the key point here is to select the correct data reduction approach for analyzing these tests.
Yep, thank you. One more question that can you conclude for different type of adhesive, what properties will be most important to determine the fatigue life of the joints, and what's the physics behind that?
For
the fatigue life, what's the parameter that we can, or what's the property that we can say, well, this adhesive will sustain longer, and this one, I know it's quite generic.
Yeah, it's very general question. I have actually some slides just to show you. For example, this one. I said that even without any experiments, and you are able to have a very rough idea about the total fatigue life of adhesive joints for different type of adhesives. And but in real scenario, we have very complicated geometry and loading conditions, and it will be difficult to have like a rough idea about that. But loading condition, frequency, all these parameters that actually I mentioned here are very important. So we cannot have a very general, let's say, conclusion saying that which parameter is the most important one. But one of the important parameters, of course, is the maximum fatigue load. And this load ratio, if you are close to the static strength of the same joint, the life will be short. For example, if you are above 80% of the static strength in fatigue loading, you are very close to like 1,000 cycles or something like that. If you are at 50%, you are close to between 100 or 1 million. If you are loading at lower than 50%, the life can be over 1 million cycles. If you keep the rest, the other parameters the same, actually.
Yeah, I think this is for the testing parameter and so on. But I think the main question here, it's a property of the material. Which property of the material that we can you say that this is the most important in determining the fatigue life of this joint? Let's say, is it elastic modulus or strength, yield strength? I don't know, plasticity, or I don't know. Have any idea about which material property we can, well, let's say we can characterize this adhesive. If it's have a high elastic modulus, we say that the fatigue life for this one it will be quite good.
If it's SN based, if it's a brittle one, so of course the maximum tensile strength. And in case you are talking about a load control scenario, in case the joint is subjected to a displacement control, then probably the stiffness can be the most important one, because you can simply reach to the final actually strength or limitation of the joint. In case we are talking about fatigue crack growth, probably then we might have large deformations. So in that case, the propagation is not controlled by stress itself, but by energy, which is a combination of stress and strain. And strain at failure can be an important parameter. So again, I cannot make a general conclusion, but stress, maximum tensile strength for more brittle ones, and for SN-based approaches, and for more ductile ones, and for fatigue crack growth, probably the maximum elongation at failure.
Yeah, this makes sense, I think. Another question is, how can this SN curve applied if the joint exposed to different temperature in real life?
Yeah, it highly depends on the parameter that you select as effective. Here, for example, we have this parameter that can take into account the effect of temperature as well. It means that when we change the temperature, actually we are changing the behavior of the material. It's like testing another adhesive, you know. And in case actually you know what are the important parameters, and that can change the fatigue life, And another important question that must be answered here is that where this parameter must be measured in the joint. And if you can correctly and properly address this and answer these questions, then you can change the temperature and just check the stress level at a critical distance, and use this stress level and stress component and strain components to actually obtain the S effective. And yeah, so this is just a matter of this parameter here. So in case you can select and develop a good one, so you are on the right way, and you can predict the fatigue life for high temperature as well.
Okay, thank you. I think we have still a couple of questions. I'm not sure if you have more time, because now we are almost 1 hour. If we extend it to 10 minutes to cover these two questions, it could be fine.
Yeah,
be good for all. Yeah, thank you. So one question that we can use your model mostly for material qualification or selection. Is it right? Yeah. And the model is mostly based on interlaminar shear stress.
For interlaminar, you mean for composite materials?
I think for the interlaminar shear stress of the adhesive joint. No, but it's yes. So now we are talking about the joint. I think it's
Okay.
the shear strength of the joint.
Yes, you mean
Yeah.
actually the thing is that for material selection, single lap joint probably can be an example because we see a lot of results in the literature. So we have a very good database for single lap joint results, for single lap joints, and by testing performing a single lap joint test, we already have an idea about the properties of our adhesive compared to other adhesives available in the literature, and then we can select the material. But since the joints are mainly subjected to shear, yeah, I think this can be a single lap joint, and shear testing can be actually a good choice for material selection.
Good, thank you. I think there is a question asking that, well, can we share this slide? I think we already have the permission to post this on YouTube, this record, yeah?
Yes.
On our web, yeah, on our channel. So just we refer to this channel for the ENERCOMP to get the recording for this webinar. So one more question. It's does the material composition and thickness affect the results?
Yes.
Thickness of the adhesive bond line and the composition of the adhesive and so on. For sure, I think it's for sure it will affect. In composite glass fiber product, we have different glass orientation and different material used in manufacturing the product. I think now we understand. No, the first question was about the substrate, not about the joint. And mostly the model we are talking about now, it's about the adhesive joint, not about the substrate. So we don't deal with the substrates. Yeah.
No, just adhesive joints. Yeah.
Okay. And one last question: can this life prediction model can be applied with the mode 3 tearing phenomena?
Which model? This model that I'm showing here?
Yeah, the SN for SN model.
Yeah.
Oh, yeah, for example, this one.
This one we have not tried, but mode 2 and mode 3 are pretty similar in terms of response, but we have not honestly tried mode 3, and we need to see if it works for mode 3 as well.
Okay.
But bond life itself is not limited to mode mixities, and if we find a model that is good for mode 3 as well,
probably,
we can include it in our software. Yes.
Okay. And the same question, continuation for this, it's can this destructive testing be transferred into NDT technique for advanced composite structure like pressure vessels? I think the question here, it's if there is a NDT or this kind of fatigue life prediction that we measure the crack and then we get the SN curve, can we find the NDT non-destructive testing technique to characterize this kind of crack propagation or the crack length, and then to apply it to advanced composite structure like pressure vessels?
You mean that using NDT to measure the crack size cycle by cycle and then be able, yeah.
Yep.
Yeah, this is another technique to measure. It's not, I don't know if we can call it NDT or not, but yeah, there are different techniques that we can use for measuring the crack size cycle by cycle, and we characterize, yes, the adhesive joints.
Okay. Thank you. I think with this, we answered all the questions that we come to. It was a very interactive session where we received a lot of questions. Dr. Ali has answered all of them in a very clear way to all of us. The seminar and the webinar, it's enriched our knowledge a lot about the fatigue life prediction of adhesive joints. Thanks for all the attendees to be here. Thanks, Dr. Ali. Thanks, Professor Lucas, for being here and the webinar. We really appreciate.
Our pleasure. I hope we can collaborate in the future.
For sure. Thank you. Thanks. Thank you, everyone.